diagram. When you see the phrase transfer function, what does that make you think of? When you see parentheses S, what does that make you think of? Laplace domain. We're going to draw stuff in the Laplace domain here a lot of this semester. Now, you follow the instructions right there? Raise your hand, state your name and your team name. Stand up with a loud and clear voice.
Did you say it in Spanish?
Pardon?
I need to say this in Spanish. You want me to say it in Spanish?
Yeah, does it say that? Oh, you have a question?
Yeah, just, I'm thinking about building. I'm not sure about this word.
Cuando. Cuando.
¿Cuándo? The building.
Oh, edificio.
Edificio. ¿Cuándo este edificio fue construido?
Does everybody understand that? Say it again louder, real clear.
¿Cuándo este edificio fue construido?
2003. 2003. I'm answering your question. 2003.
Oh, doesn't
Yeah. 2003. Now, what did we just do? We had a conversation in a language other than English. Laplace domain is just a language other than time domain. Time domain is the experiments that you've run so far in the lab. Time domain is the experiments you're going to run all semester in the lab. But the analysis that we're asking you to do is in the Laplace domain. Isn't that sweet? Everybody says, sweet, Dr. Indy, because we're learning a lot about Laplace domain, and we've learned it in the E-course, right?
Sweet.
All right, here's the kind of graphs you're going to get in week 3 experiments, and I'll show you a real one in a minute. Time domain in this axis. All semester, your experiments are going to be time domain on the x-axis. And over here, there's something C, that means the controlled variable as a function of time. This is a time domain graph. And this is a graph according to this function, 1 minus e to the minus little t over capital T. Capital T is this unit, and little t is a parameter. And then there's a line here that is tangent to this line down here. And it comes up here and it has a slope of 1 over the reciprocal of t, according to this. So you're going to see graphs similar to this with different time axes and different y-axis. But you'll see that over and over again. Anybody know why this 0.632 is a line here rather than 0.6 or 0.5 or something like that? Not even 2/3.
That's when half of you reached halfway point of your temperature change.
You're saying, what's temperature, this thing?
One time constant.
Oh, it's one time constant. Yes. So, somebody have a calculator? Plug in 1 minus e to the minus 1. This would be, if this is capital T, then this will be 1. 1 minus e to the minus 1. How much? 0.632. Magic. It's one time constant. Its experiment will go 63.2% of the distance of the. What do you think about this one? This says step response. This is amplitude of your output. This is time in seconds. By the way, these last two graphs are straight out of your book, I believe, chapter 2 or something like that. This one doesn't have the same form as that other one, does it? This thing here we call overshoot. This we call the final steady state value. Let's go back one. This is the final steady state value. After 5 time constants, it's so close to 100% that we call that 5 time constants. It gets to 100%. Some people say 6, but I don't care. Time constant, by the way, little t, is one of the things that we're going to be learning this week in your experiment. There's 3 things you're going to be learning. One of them is the time constant. And in my lingo, I always use a Greek letter tau for that. So I'd like you to use a Greek letter tau for time constant. Oh, that was, this, sorry. This t, I would use tau, and this t is time. If that's confusing to you, I can clarify it later maybe. So here is one that doesn't. Oh, this is the final steady state value. There's a tangent you can draw here to the steepest point. Notice that the steepest point is not right at the origin, it's somewhere else. Notice that? There's a little curvature there. Notice that, Sarah? Mm-hmm. And then it goes over the final steady state value. We call that overshoot. Everybody say, that's overshoot, Dr. Henry. Y'all are so good. And then it comes under it a little bit, and then it settles down. And we would call this the settling time. Call this, so that's the settling time, Dr. Henry, when it finally reaches steady state value. And how picky are we about final steady state value being exactly final steady state value, 100%, 0.0000? Pardon? No, we're not exact. Just look at the graph. Ballpark it. That would be 2.5 seconds, something like that. I'm not picky. Let's see what the next slide is. Here is an experiment, an actual experiment run by one of your class members a couple of days ago. Real eager beaver. Even before I described all this stuff, this student went in and clicked on week 3 experiments and said to do this, and he did it. So here's an experiment. There's a blue line that's input, a red line that's output. This is flow. It's one of those teams in the back, right? You're on flow. You're on flow. Just those 2 teams, I think. And here's an experiment that ran for 30 seconds. And the input's over here, right? Well, that's the output. Sorry, the input's here. So it started at 31%, and after 15 seconds, it went to something here, maybe 61%. So the step size is how much if it goes from 31 to 61. Y'all are good. Y'all are fast and good. 30. You with me, Jerry? You with me, Ben? You knew that. And it occurs at 15 seconds. Now, all this stuff over here, I don't care about. The computer will give it to you, but don't give it to me. So if you put this in a report or a presentation, scratch that out. It's uninteresting. It's startup transients. We're not interested in that. We're interested in just getting to some steady, more or less steady value. Does this look like a steady flow for a flow system? I mean, it's not perfect, right? It's not like those graphs I showed you. And then it reaches some steady value over here, so let's say 25 seconds it's steady. Cross all that out, and maybe before 10 seconds. So I would crop this between 10 and 25 seconds in doing the analysis. From this curve, we can get 3 parameters. One of them is the time constant, which I like to call tau. That's the thing that, when it's tau, it goes up 63.2% of this distance. You with me? Can you review that? Raise your hand if you have a question. We're fitting this curve, this mathematical curve, to that experimental curve. And after it goes up 63.2% of where it started to where it ends, then that amount is tau on the time axis. What do you notice different between this graph and that experimental graph? Okay. No, we're not talking, so I'm going to give you a team assignment. Get together in your teams and come up with 3 differences between this graph and the other. Go. Why don't you move over there and read it? Tell me your name. Are you supposed to be in this team here?
It's not working, is it?
Do what?
So we need to get back to like 50 to 60 days.
You're Alex. Let's get with this team for this purpose.
We're going to do that one last week when we were in the lab down there, and I ran that perfect graph. And he called me in there.
You gonna use that graph?
I can't. It's not in my range. It's in his range. So,
Well, I never reached my range. He said it was mine. So,
I didn't come up high enough this time. So,
In the last one.
Yes, yeah, but, oh, you want to see the other one? Excellent. Stand up and state your name and your team name.
Dave Freeman, pink team, we wanted to see what the other graph is. Thank you.
You're welcome. One clap for. Who needs more time? Raise your hand. All right, which team wants to go first? How about here? What team color are you? Green? Representative from Green? Listen up. Representative from Green is going to stand up and state their name and the team name and say in a loud and clear voice the differences between these 2 graphs. Just one. Unless you can speak in unison.
I was saying 1 reason or 3 reasons?
All the reasons.
All our reasons? All right. John Dover Green Team, we said that, which I don't remember the first one, so I'll give you 2. We said that it goes down and goes back up. This one just immediately increases from its starting position. The other graph went down, had a steady state, went back up. Also, this graph has 1 steady state, the other one has 2. That's right. How abruptly the other one changes, yeah.
Say it again.
The other one changes abruptly. This one's kind of smooth, gradual change.
One clap for John. Another team. What, David, your team back there. David and Christo and Aaron and the other one, whose name I forgot. Stand up, state your name and your team name. Y'all are next here. Y'all are coming up next. You think I'm ignoring this side of the room?
Chris, our gold team, this graph has a defined slope. Everything's defined on the graph itself, visually.
Say it again. Loud and clear voice.
The first one you had up there had
Yeah.
everything defined, all the labels on it with the, nice little one with the towel. And also we noticed that, this one has two city states. Unlike the first one, there's one. And this is not smooth.
This is not smooth, the other one's smooth. The other is mathematical, this one is experimental. Okay, one clap for Chris. Who has something really neat over on this side of the room? Oh, come on. Yes, stand up and state your name and your team name and give the answer to the question. What's different for you?
Marion is the Ira team. The second one has two set of data. There is the output and the input.